is the day 2, and we're today going to learn about the memory segmentation that the modern operating system and compilers implies, and we're going to learn about the registers in 8664 architecture processors or 8664 microprocessors, the registers and the types of registers in such microprocessors, and the basic some few theories also, and we're going to see it practically using the GDU. So let's get started. Okay, first, first close this. Let's open Droid.io. Let's create this new. Let's call it day 2. Okay. So what is computer? First, let's talk about what is computer. Do you know what is computer? Computer is an electronic machine which is used for. We use it for the input, and then process, and then output, right? So we need computer to process things, and who does the processing? The processing is done by the CPU, central processing unit. Let's call this processing. So okay, so this is the very basic of the computers. A computer is an electronic machine that is used to input the data, process it, and output. And who does the processing? CPU. Yes. And then who does CPU take data from? CPU is very close to the. Let's call this RAM. So RAM is the only memory that is closer to the CPU, and then yes, CPU reads data from the RAM, CPU writes data to the RAM. So that is why everything in computer, since RAM and CPU are very close, and in order to process anything, CPU needs RAM. CPU reads the input from the RAM, input or the program from the RAM. We need to load everything in the RAM. That is why we need to load everything into the RAM. Yes, including the operating system as well, right? So I think you are familiar with this, that the operating system also needs to be loaded at the RAM, right? Because RAM is very important. RAM is also known as the primary memory or the main memory, and it is very close to the CPU. And RAM is the only memory that the CPU directly interacts with. That is why everything that we want to be processed needs to be loaded into the RAM, right? So let's take it to the C context. Okay, so we saw that hello world program, uh, hello.c program, right? So I compiled it using the gcc output hello.c, right? So I compiled it, then if I run it, then it will will run this it will run this hello executable, right? So what's really happening is, in order to run it, we have to first load it into RAM, right? Because running it means like giving it computational power, engaging it with the CPU. That's why we first need to load it into the RAM. This file needs to be needs to be needs to be loaded into the RAM, right? So uh, we have our program, and then we have our, let's call this RAM, and then let's call this process. So whenever a program is loaded into the RAM, then it becomes a process. Are you understanding what I'm saying? So a program is just it's just a set of instructions that is stored somewhere on the hard disks. But whenever a program is loaded onto the RAM, then it becomes process, right? So when a program is loaded into a RAM, certain memory is allocated for this program, and yes, certain memories allocated in this program. Yes. Okay. So whenever a program is loaded into RAM, certain memory of the RAM, certain portion of the RAM is assigned to that program, which is what we call uh, memory segmentation. So what happens ki, our program is separated, is given, is assigned a memory, is allocated a memory, and then the memory is further segmented into following categories. For instance, the first is the first, and at the top is our stack, right? So stack is at the top, and then we have heap, and then we have BSS. BSS, and then we have data segment, and then we have text segment. This is best BSS segment, and then we have our heap, and then we have our stack, right? So yes, memory segmented into following sections, memory segmented into following sections, and the starts stack segment. uh, yes, the stack segment stores the local variables, function, return type, function parameters, everything that is related to the function is stored into this stack. Is stored into the stack. Similarly, heap heap is used to store the um, very large chunk of data. Yes, very large chunk of data that is they are stored in the heap. And then we have, yes, BSS. So BSS segment stores the uninitialized global variables. So if we have any global variables in our program that is uninitialized, then that is stored in the BSS segment, and then the data segment stores the initialized is global variables. So data stores the initialized global variables. Similarly, we have text. Yes, so it's very important because text stores the actual instructions of the program. actual instructions of the program. So yes, text actually stores the actual instructions of the program. For instance, if I'm writing a program to print something on this console, then the instruction to print the uh, any character or anything on the console, that instruction is stored on the text. And if we have defined any global variables within our program that has been already initialized, then that is stored in the data. Similarly, if we define any global variables that hasn't been initialized yet, it's stored in the BSS. And heap is used to store a large chunk of data. Stack stores the local variables, function return type, function parameters, etc. Parameters, right? So this is what we are going to see through the GDB. Okay, so let's go to the desktop. Okay, so memory, yes, memory segmentation. Let's see. Okay, so I'm going to include int main, right? Return 0, and let's say int int number is equals to 28, and then I'm simply going to print f percent number. Okay, so I'm going to compile it. Memory segmentation.c. Okay, so this okay, so this here, memory segmentation, and they are the programs, because it hasn't been loaded into the RAM yet, so they are the programs. So whenever I do this, if I press enter, it will be loaded into the RAM, and the memory will be allocated to this program, and the CPU will execute it, because CPU only directly interacts with the RAM, right? So if I do this, yes, the CPU has processed it, and 28 has been printed out. Okay, so we are going to see what's really happening inside it. So I'm going to open it with the ZDB, yes, ZDB memory. Okay, so I'm going to list it. So this is our program, right? And then okay, so now I'm going to this. Yeah, no. First, let's look at the memory segmentation. So we can look it by info files. So you can see that text, right? So text segment, as we can see that text segment stores the actual instructions of the program, right? So we are going to look at this. So it is at the 1050 location, hexadecimal. Yes, the text segment starts from the 1050 and it ends at the 1168. That means how many bytes does text segment occupy. You can find it, hex calculator. I think calculate here. 1168, 1168, and then 1168, 1050. Sorry, 050. We're going to find the difference. Okay, difference, and then we're going to calculate. Okay, so there it occupies the 280 bytes in decimal. So we're going to see this x see that all these are the instructions, actual instructions of our program. uh, these are our instructions, these are our instructions, and they are being stored into the text segment. We can see that, right? We can see that it has these are all the instructions. Yeah, they are all the instructions, and we can see that here is our the main functions, main function. Yes, our main function, the all the instruction related to this are stored in this section from this memory 1140 okay. So I'm going to see like 20i, the main starts at 1140, so it starts at 1140. Okay, so these are the instructions of the main functions. We can also verify with the this symbol main. Yeah, they are the same, right? So yes, we can see that the text store text stores the actual instructions of the program. Data stores the initialized global variables, BSS. uh, yes yes, here is our BSS segment, here is our data segment, here is our text segment. Yes, because we haven't pushed anything onto the stack, the stack is not here, so we can also see the stack from here. So let's break min. I'm going to run it. The stack is at the so we can find the memory of the stack pointer. So it's pointing db50, right? So I want to see the 10x from the $RSP. Okay, so db50 is the stack pointer, but here is a very good trick, because stack adds lies at the this is our high memory address, and then this is our low memory address. Okay, so the memory goes on increasing. So the text segment has the lesser memory address, then it goes on increasing. But this stack, but we know that stack and heap, just in here, so stack and heap. So what really happens is stack moves this direction, whereas heap moves this direction. Okay. Yes. So our stack, uh, yes, stack. If the stack is being, if something is being pushed into the stack, then it will increase in this order. It will go from the high memory address to low memory address. Since there is nothing in this stack, our stack pointer is at the higher memory address, and all the stack values are the available stack space are at the low memory address, right? So since db50, since RSP, but we want to see the lower memory address, so I'm going to do -30. Okay, so we can see that all of these are zeros from, right? So these are the space that the stack can occupy, right? In this way, yes, we can see that there is a stack also, heap also, BSS segment, data segment, text segment, etc. Alright, so yes, now uh, practically we have practically seen the memory segmentation implementation into our memory. Now we're going to talk about the 8664 microprocessor registers. Yes, there are several registers in microprocessor registers. There are several registers. So there's RAX, RSI, RDI, RBP, RSP, right? And there are other registers. These are EAX, ESI, ESI, EBP, ESP. So there are these registers as well. So RSI, RAX, RDI, they all are the registers for this 64 bits operation, that is 8 bytes, right? The 64, yes, they are only used if there is a 64-bit operation, 8 bytes, and then if they are used if there is 32 bits, 32 bits operation, that is 4 bytes. So if there is any 4 bytes operation, then these registers will be used. If there are 64 bits operation, 8 bytes, then these operations will be used. So we can see that as well. Yeah, these are the registers of the 8664 microprocessors, and it's very common nowadays. So let's go here. Okay, let's do for this program. So I have declared a variable initialization. Also we can variable variable initializations, and we know that int occupies 4 bytes, right? So 4 bytes. So for the 4 bytes, our processor is going to use EAX, ESI, EDI, right? And then printf function. So while if we have talked before that the first argument is always stored in RDI, second in second in RSI, right? So our percentage d should be stored in RDI and number in RSI, right? So this is what should happen. Yes, this is what should happen. So we're going to see this. We're going to let's create it. Yes. Again, let's do this in GDB memory. I'm going to disassemble main. Okay, so you can see that yes, it has been pushed onto the stack pointer pointing to the base pointer. Now yes, now we are subtracting stack pointer to the by the -10. Yes, so subtracting, yes, since yes, so stack is here. So let's make a stack. Yes, let's make a stack. starts from the high address memory and it's to the low address memory, right? So at first, at the initialization, our RBP and RSP point here, right? So yes, they point here, they point at the bottom of the stack. But now, since yes, RSP has been subtracted by 10, means like it will move to the lower memory address. Since RSP has been subtracted, it will be less, so it will move to the lower memory address. So RSP will be by how much? By 10, by 10, 10 hexadecimal, which means 16 decimal. So by 16, so so now our RSP is going to point here, uh, and then the gap is 16 bytes. So here the gap between 16 bytes. So there are 16 bytes between the RBP and RSP, and now RSP is not, it's no longer pointing here. So yes, so this is what happened with this line. And now it says that RVX move 0x1c hexadecimal value to the point, okay, 0x1c hex to decimal is a 0x1c so 28, it is equivalent to 28. So it's moving 28 to the location RBP minus 0x4, which is equivalent to 4. So yes, so RBP minus 4 bytes. So here let's draw, yes, let's keep it here. Control Z. Okay, so now exactly clear. It's a straight line. So okay, so here is 4 bytes. Let's duplicate this. 1, 2, 1, 2, 3, and then 4, right? So RBP. So RBP is pointing here. So RBP minus 4, 1, 2, 3, 4, 4 bytes. So from here we are storing the 9. We're storing 28 value. Where are we storing? We're storing it in this section. So yes, RVX minus 4. So let's label it as well. RBP minus ZX4. Yes, so this is where our 28 values is stored. RVX minus Z4, and then now moving the RVX minus Z4 value to EAX. So now EAX is pointing to the 28. Now yes, our EAX is pointing to the 28, and then after that we are moving 20 to the ESI. Yes, so now ESI holds ESI is pointing to this location, right? So ESI is pointing to the 28, and then we are loading the content at this at the RAX. So let's see what's there. X string dollar RIP plus 0x EVO. Sorry, 0x EVO. No registers because let's break it. Run next I RIP. It's at line 18. So now RIP is at line 20. So after no, first let's look at what is the content at the RIP plus 0x EV0. So there is a string, right? So I'm going to execute the next command, and then I'm going to see what is actually at the RAX. So yes, now our RAX is storing the percentage D, and our ESI is storing. So RSI storing percentage, sorry, percentage D, and then our ESI is storing the 28, right? So ESI is storing 28, and then we have for yes, for the printf function, the first argument should be stored in the RDI. Okay, so this is done, and the number should be stored in the RSI, and number in RSI, right? And then and the number second argument should be stored in the RSI. But since it is a 4 bytes 4 bytes number, RSI doesn't deal with it. ESI deals with it. We have already talked about this here. Yes, for the 32-bit operations, 4 bytes ESI is used. That is why it has been, the value is being loaded in ESI, and then we have now RDI and then ESI. Then we are calling the printf function, and that's how the 28 is being printed onto the terminal. So if I do memory, then yes, 28. So yes, that's how the registers at the 8664 microprocessor works. That's how variables are works. And we talked about the memory segmentation. We talked about why everything needs to be loaded into the RAM, and what happens when a program is loaded into the RAM. What are the stack segment, heap segment, text segment, BSS segment, data segment, etc. Thank you for today, and that's it.